Hi everyone, this is Professor M. Science, and today I want to talk about the relative motion of two interacting quantum particles in another one of our videos on rigorous quantum mechanics. If you've been following our videos for a while, you may have noticed that all of our videos on the postulates of quantum mechanics, or angular momentum, or the quantum harmonic oscillator, they all focus on problems with a single quantum particle. So today we're going to take a very exciting step forward and talk about what happens when we have two particles. This will provide the foundation to study one of the most iconic potentials in all of quantum mechanics, the hydrogen atom, which is made of a proton and an electron. What we're going to learn today is that quantum systems of two particles can actually be solved with what we already know about quantum systems of a single particle. This is because we can apply a very convenient change of coordinates that will take us from our system of two real interacting particles to another system of two fictitious particles that don't interact. And we can then treat these two non-interacting particles as two individual single particle systems. So let's go! To set up the problem, let's start with a coordinate system. Before we do anything else, let me emphasize that our discussion will be general and apply to particles moving in a three-dimensional space. But for clarity and simplicity, I'm going to draw two-dimensional diagrams. Let's consider a particle at position R1 with mass m1 and another particle at position R2 with mass m2. The focus of today's video is to study two-particle systems such as this one. In particular, we're going to focus on a very common situation, which is what happens when these two particles interact via a potential V that only depends on the relative position of the two particles, so we can write it as V of R1 minus R2. Two-particle systems are very common, and many of you will have encountered them before in the context of classical mechanics. What we'll do today is to explore the corresponding quantum two-particle system, and we'll find that we can effectively rewrite it as a system of two fictitious particles that do not interact with each other, something that greatly simplifies the maths. Today we're going to look at the general properties of two-particle systems, but moving forward, one key system that builds from this video is the hydrogen atom, in which these two particles are a proton and an electron, and their interaction is described by the Coulomb potential. So I encourage you to check out all of the videos on the hydrogen atom afterwards. If we start with particle 1, then in quantum mechanics we have 3 position operators and 3 momentum operators. I'm using the subscript 1 to indicate that these operators are associated with particle 1. As always, the position and momentum operators obey the canonical commutation relations, which we have along the first direction, along the second direction, and along the third direction. And any other commutator involving operators associated with particle 1 vanishes. Similarly, for particle 2, we have 3 corresponding position operators and the 3 corresponding momentum operators. We also have the corresponding 3 non-vanishing commutation relations along the first axis, the second, and the third one, and again, any others involving particle 2 operators vanish. Any mixed commutators involving an operator associated with particle 1 and an operator associated with particle 2 also vanish. To put it another way, we have 12 operators grouped in 3s, here, 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 and here. Then all commutators between these 12 operators vanish, apart from these 6 commutators written down explicitly here and here. To make progress, we're now going to define 2 new sets of coordinates. The first are the center of mass coordinates. I label them with a capital R, and define them as the mass-weighted average of the original coordinates. Pictorially, we can draw a coordinate system again, place particle 1 here and particle 2 here, and the center of mass coordinate is a mass-weighted average of the positions of the two particles. So for example, it would be somewhere between the two particles here. And this example corresponds to particle 1 being heavier than particle 2, so the center of mass is closer to particle 1. If you're familiar with classical physics, then you will recognize this definition. If you've not encountered this before, don't worry. You can simply take this as a definition, and what we will discover today is that the center of mass is a very convenient way of describing two-particle systems in quantum mechanics. Before we move on, and just to be absolutely clear, this operator capital R is in reality made up of three separate operators capital X, capital Y, and capital Z. Each of these in turn is defined in terms of the original coordinates. For example, X is equal to this. The second set of coordinates we need to define are the relative coordinates. We're going to label them with a lowercase r and define them as the relative vector between the two particles. Note that I'm using lowercase r's for all of these coordinates, but when I have a subindex 1 or 2, they refer to the positions of the particles, and when I don't have a subindex, they refer to the relative positions of the two particles, so keep this in mind. If we make some room in the above diagram, then the relative coordinates define this vector. And just like for the center of mass coordinates, the relative coordinates are an operator r made of three separate lowercase operators x, y, and z. And as an example, the x operator is given by this. We can easily invert these definitions to write the position of particle 1 in terms of the center of mass and relative coordinates, and the position of particle 2 also in terms of these new coordinates. And I will leave the proof of these expressions as an exercise for you. Let's now turn to momentum, and we'll start with the definition of total momentum. To motivate the definition, let's first consider the classical setting. Classically, we would define the momentum of the center of mass with a capital P and set it equal to the total mass of the system multiplied by the time derivative of the position of the center of mass, where this dot indicates the time derivative. We can now expand the total mass as the sum of the masses of our two particles. And using the definition of the center of mass position, we get this second term. We can now cancel this term with this term and end up with m1r1 dot plus m2r2 dot. This is simply the classical momentum of particle 1, and this is the classical momentum of particle 2. By analogy, we'll now define the total momentum operator in quantum mechanics. We also label it with a capital P and set it equal to the sum of the individual momenta of the two particles. And again, remember that this is in reality a collection of three different operators. The next quantity, as you may suspect by now, is the relative momentum. In classical mechanics, we label it with lowercase p and set it equal to mu times the time derivative of the relative coordinate. This mu here is called the reduced mass and is given by m1, m2 over m1 plus m2. We then also have the time derivative of the relative coordinate. Reorganizing this expression, we get this. And now this term in brackets is the momentum of particle 1, and this term in brackets is the momentum of particle 2. By analogy, we will now define the relative momentum operator in quantum mechanics. We also label it with a lowercase p and set it equal to the classical expression where the momenta are promoted to the corresponding operators. And again, just keep in mind that this is in reality a collection of three different operators. We can easily invert these expressions to obtain the momentum of particle 1 in terms of the center of mass and relative momenta, and in a very similar way, we can get the momentum of particle 2 in terms of the new momentum variables. And I'm going to leave the proofs of these relations as an exercise for you to try out. As we already discussed earlier, if you've encountered these relations before in classical mechanics, that's great. But if you haven't, don't worry. You can simply take the various equations as definitions, and we'll find out later in the video that these definitions turn out to be very convenient when working with two-particle systems. Okay, so we've had enough definitions, so let's recap. We're studying a two-particle system, and to describe it, we have used this collection of operators associated with particle 1 and this collection associated with particle 2. Each of these operators is made of 3 components, so we have a total of 12 operators. Then we have defined a new collection of operators, the center of mass operators, and the relative operators. And this is simply a change of variables, and as expected, we still have 12 operators. Overall, we can describe our system with either set and then relate them together with the appropriate change of variable formulas. What we will see today is that this second collection of operators is the most useful to describe a system of two particles interacting via a potential that only depends on their relative position. The first step is to realize that this new set of variables behave like the usual position and momentum in quantum mechanics, in the sense that they obey the standard canonical commutation relations. Like for the original set, all commutation relations are 0 apart from the 3 for the center of mass variables along the first axis, the second axis, and the third axis. And the equivalent 3 for the relative variables, starting with the first axis, and the second, and the third. To check that these commutation relations are true, let's use the commutator of x with px as an example. First, we insert the definition of x in terms of the original variables, and then the definition of px in terms of the original variables. We can expand this commutator to get first the common factors, and then 4 terms proportional to various commutators. The first one between the position and momentum of the first particle. The next is between the position of the first particle and the momentum of the second particle. Next, between the position of the second particle and the momentum of the first particle. And finally, one between the position and momentum of the second particle. We can cancel this commutator and this commutator because they are between different particles, so they're equal to 0. This one is IH bar, and so is this one. Putting everything together, the original commutator finally gives IH bar. And this confirms this first commutation relation here. The rest are equally simple, and you can work through the derivations yourselves if you want to get some practice. Overall, we can work in terms of the original coordinates given by this collection of 12 operators obeying the canonical commutation relations, or in terms of this new set of 12 operators which also obey the corresponding canonical commutation relations. This type of change of variable is extremely useful, as we will see in the rest of this video. We're now ready to look at the Hamiltonian of our system. We have the kinetic energy of particle 1, the kinetic energy of particle 2, and then their interaction energy, which depends on the relative position of the two particles. Before we move on, we need an important clarification about notation. If you've already seen the video on tensor products, then you will know that this Hamiltonian acts on the state space W of the two-particle system, which is given by the tensor product of the state space W1 of the first particle and the state space W2 of the second particle. Now, when we spell out the Hamiltonian like this in terms of 3 terms, then each of these terms must also act on that same tensor product state space. To be precise, this means that the kinetic energy operator of the first particle should really involve the tensor product of P1 squared with the identity in W2, and the kinetic energy operator of the second particle should have the corresponding tensor product. While these expressions involving tensor products with identity operators are the technically correct expressions, we typically use the shorthand where we omit the identity operators and the tensor product, and simply use this expression for particle 1 and this expression for particle 2. This is the convention that I'm going to use today moving forward, and only go back to the full expressions when necessary. Before we move on, if you have not heard about tensor products before, I would really encourage you to check out our video on tensor products right now. It's a very important topic when we consider systems of more than one quantum particle. So for now, let's make some room and go back to the problem at hand. We want to rewrite this Hamiltonian in terms of the center of mass and relative variables. For the kinetic energy terms, let's first consider the square of the momentum of particle 1. Using the expression that we derived earlier about this momentum in terms of the center of mass and relative momenta, we can rewrite it like this. We can now calculate the square, and we get 3 terms, one proportional to the square of the center of mass momentum, the other proportional to the relative momentum, and then in principle we would get 2 cross terms, but we can combine them into one because the center of mass momentum variables commute with the relative momentum variables. Using a similar derivation, we can rewrite the square of the momentum of the second particle as a term proportional to the total momentum squared, a term proportional to the relative momentum squared, and a cross term. We can now go back to our full kinetic energy, which is the sum of the kinetic energy of particle 1 and the kinetic energy of particle 2. Using the expressions that we just derived, we start by combining the total momentum terms here and here. We get this prefactor multiplied by the total momentum squared. Next, we combine the relative momentum terms here, and we now get this prefactor times the relative momentum squared. The cross terms here and here cancel because of this minus sign. And you might want to stop here for a moment, pause the video, and just cross-check that you're happy with these steps. Right, moving on. This here is the total mass of the system, and this here is the reduced mass of the system. Putting everything together, we can rewrite our full Hamiltonian in terms of a kinetic energy term that depends on the total mass of the system and the total momentum squared, another kinetic energy term that depends on the reduced mass of the system and the relative momentum squared, and we cannot forget the potential energy term, which is trivial to rewrite in terms of the new coordinates. Its argument is simply the relative coordinate. Let's take a step back and see what we've accomplished by changing coordinates. The original Hamiltonian has these 3 terms. When we rewrite it in terms of the new center of mass and relative coordinates, we also get 3 terms. In both cases, we have 2 kinetic energy terms associated with each type of momentum. In the original expression, the kinetic energy terms depend on particle 1 of mass m1 here and particle 2 of mass m2 here. And in the new expression, we also have 2 kinetic energies. The first one here looks like the kinetic energy of a particle of mass capital M, the sum of the masses of the original particles, and is given in terms of the center of mass momentum capital P. The second here looks like the kinetic energy of a particle of mass mu, the reduced mass of the 2 original particles, and depends on the relative momentum. This result is really extremely important. Looking at the kinetic energies of the transformed Hamiltonian, mathematically they look like the kinetic energies of 2 particles, one of mass capital M and the other of mass mu. So if this is what the maths tells us, we can then also extend this to the conceptual level. We can think of this system in terms of the original 2 real particles of masses m1 and m2, or equivalently in terms of 2 new fictitious particles of masses m and mu. The question you will probably have at this point is, why would we want to think in terms of these 2 fictitious particles rather than in terms of the original particles? And the reason is the potential term. While in the original expression, the potential energy depended on both position coordinates r1 and r2, the potential energy in the new expression only depends on the relative coordinate r. And this is critical, because while the 2 original particles interact with each other, the 2 new fictitious particles do not. And this makes the solution of the problem much simpler, because we've transformed it from a problem of 2 real interacting particles to a problem of 2 fictitious non-interacting particles. In practice, this means that we can now separate the Hamiltonian into two non-interacting terms. We define a center of mass Hamiltonian that only has a kinetic energy term, and we can define a relative Hamiltonian that has both a kinetic and a potential energy term. The first Hamiltonian describes a fictitious particle of mass equal to the sum of the masses of the two particles and moving freely in space. Or to put it another way, it describes the behavior of the center of mass of the system. The second Hamiltonian describes another fictitious particle whose mass is equal to the reduced mass of the original particles and is subject to this potential energy. It describes the relative motion of the system about the center of mass. The total Hamiltonian is simply the sum of these two Hamiltonians and describes the two fictitious particles simultaneously, but they crucially don't interact with each other. The next topic is therefore why separable Hamiltonians such as this one are so much easier to work with than Hamiltonians with an interaction term. Let's consider a state space WCOM, which is the space where the center of mass Hamiltonian lives, hence the acronym COM. And let's also consider its eigenvalue equation, where these are the eigenvalues and these are the eigenstates. Let's separately consider a state space WREL, which is where the relative Hamiltonian lives, and this is its eigenvalue equation, with the eigenvalues here and the eigenstates here. We can now construct the state space W, which is the tensor product of WCOM with WREL. The full Hamiltonian H lives in this tensor product space, and this is its eigenvalue equation, where these are the eigenvalues and these are the eigenstates. What I want to show now is that we can build the eigenvalues and eigenstates of the full Hamiltonian here from the eigenvalues and eigenstates of the individual Hamiltonians here and here, which means that we can build the solution of the two-particle system by only solving two separate one-particle systems. In particular, we will show that we can write the eigenstate psi as the tensor product of the eigenstates of the center of mass Hamiltonian and of the relative Hamiltonian, and that we can write the total energy E as the sum of the center of mass energy and the relative energy. To see this, we will first show that the tensor product state is indeed the eigenstate of the full Hamiltonian. We therefore start by writing the full Hamiltonian acting on the tensor product state. We next expand the Hamiltonian into two separate terms, still acting on the tensor product state. And from the video on tensor products, we know that this term will now only act on this part of the tensor product, as this is simply the eigenvalue equation for the center of mass Hamiltonian. We simply get the eigenvalue times the state. Similarly, this term will only act on this part of the tensor product. And again, it corresponds to the eigenvalue equation of the relative Hamiltonian, so we get the corresponding eigenvalue times the state. We can take out the tensor product as a common factor, and we get this. Overall, this confirms that the tensor product state is an eigenstate of the full Hamiltonian, so we can indeed write the eigenstate psi as this tensor product. And we also immediately see that the eigenvalue is simply the sum of the eigenvalues of the two separate Hamiltonians here. Overall, this means that solving these two separate eigenvalue problems is enough to then build the solution to the full Hamiltonian up here. The eigenvalues are simply the sum of the two original eigenvalues, and the eigenstates are the tensor products of the original eigenstates. And this is why working in terms of the two fictitious non-interacting particles is more convenient than working in terms of the real interacting particles. So, we can solve the two parts of this Hamiltonian separately. Let's start with the center of mass Hamiltonian here. We can write the Hamiltonian as simply given by the kinetic energy of the center of mass. In the position representation, the kinetic energy term becomes this. And remember that the Laplacian is obtained from the gradient, and in the case of the center of mass variables, it is explicitly given by this. Putting things together, we get this eigenvalue equation in the position representation, where I'm using the standard notation for eigenfunctions. This is the eigenvalue equation of a free particle of mass M. And from the corresponding video, we know that the eigenfunctions are given by plane waves like this. And the eigenenergies span a continuous spectrum that has a dispersion proportional to the momentum squared. Overall, this means that the center of mass behaves like a free particle, and this Hamiltonian simply describes translations of the system as a whole, with all the energy being in the form of kinetic energy. We can therefore solve the behavior of the center of mass once and for all, and we've just done it. Let's now turn to the relative Hamiltonian here. If we copy it, we now remember that this Hamiltonian has a kinetic energy part and a potential energy part. And again, working in the position representation, we can rewrite it like this. The Laplacian is again obtained from the gradient, which in this case of the relative variables is given by this expression. Putting everything together, we get this eigenvalue equation in the position representation. Unlike the case of the center of mass Hamiltonian, for the eigenvalue equation of the relative Hamiltonian, we cannot provide a once and for all solution. This is because of this potential term here, which will take a different form for different systems. So, to fully solve the problem of two interacting quantum particles, we've now gone as far as we can go without specifying the form of the interaction potential. For specific examples, I refer you to our videos linked in the description, for example those on the hydrogen atom, where this interaction is given by the Coulomb potential. However, before we conclude, there is in fact one special case in which we can take one extra step. And this is the case when the potential V does not depend generally on the relative position of the two particles, but in fact only depends on their relative distance. And by that I mean the magnitude of the relative coordinate. At this point, you will probably all recognize this potential. It is the central potential. This means that what we learned about the motion of a single particle in the central potential in the corresponding videos can be directly used to describe the relative motion of two particles interacting via a potential that only depends on the distance between the two particles. You may wonder whether this is a situation that we ever encounter, and the answer is a resounding yes. The Coulomb potential is an example of an interaction between two particles that only depends on the distance between the particles. A very good way to see this in action is to check out our videos on the hydrogen atom, in which a proton and an electron interact precisely via the Coulomb potential. From our discussion today, this means that although the hydrogen atom is a two-particle problem, the relevant physics described by the relative motion of the proton and the electron is effectively a one-particle problem. And, furthermore, it is the problem of one particle moving in a central potential. So overall, we've arrived at a rather neat result. We started with a system of two complicated interacting quantum particles in which the interaction only depends on the relative position of the two particles. We've then found that we can separate this into two different problems, one for the motion of one fictitious particle which moves as a free particle whose mass is a total mass of the system and which describes the center of mass motion of the system, and the second as the motion of another fictitious particle whose mass is the reduced mass of the system, which describes the relative motion of the two original particles. This is pretty useful because rather than having to solve the original problem of two interacting particles, we now have two separate problems of two non-interacting fictitious particles, which are much easier to solve. Today, we've laid the groundwork to study systems of two interacting particles. As a good example of such a system, I would encourage you to watch our video on the hydrogen atom. And as always, if you liked the video, please subscribe.